Hello, everyone. I'm Paulito, a research scientist in Dublin Research Lab. The title of my talk is Finding an Effective Strategy for AutoML Pipeline Optimization. Before anything else, I'd like to acknowledge my collaborators, Akihiro, Rado, Elizabeth, and Pari. The problem that we are interested to solve is to find the best machine learning pipeline in a given prediction task. Most approaches uses cache strategy or combined algorithm selection and hyperparameter optimization. And these are the top algorithms and most popular ones. The cache problem can be decomposed into three major components. The first component is finding the best among n models, which require n of m search space. The second is the search for the best order of p processing elements, which is n of p search space. And lastly, searching the best among h hyperparameters, which require n of h search space. So all in all, the cache time complexity will be the product of n of m times n of p and times n of h. In our proposed approach, we would like to reduce the complexity of the problem from multiplication into addition, so that we will only be dealing with n of m plus n of p plus n of h search space. So we can do this because our search will not be simultaneous, but done in stages, where stage one will be model selection using an arbitrary pipeline. Stage two will be pipeline selection using the best model in stage one. And stage three, which is optional, will be hyperparameter optimization of the pipeline in the model found in stage one and stage two. Before we go on doing the implementation, let me discuss some preliminaries and reformulate the problem in terms of pipeline blocks. This will be a simplification of the problem, but we hope that the simplification will reduce the search space, but at the same time will not affect the performance. So let me start with some assumptions. So let's assume that we have a set of scalars, such as min-max, robust scalar, standard scalar, and many others, and a set of feature extractors, such as PCA, ICA, and FA, and a set of learners, such as random forest, XGBoost, AdaBoost, and many others. And let the expression x for pipe f to be f of x, and x plus y to represent the concatenation of features x and y. So with these preliminaries, we can now define pipeline blocks, where the one block pipeline is composed of a scalar, an extractor, and a learner, while a two block pipeline is composed of a scalar and an extractor, plus another scalar and extractor, and feed to the learner. If we represent a combination or the pipeline of SC pipe to XT as PRP, we can represent an n block pipeline to be the summation of PRPs from 1 to n, and their aggregation using the plus. The resulting aggregation will be fed to the learner. So with these preliminaries, I think we are now ready to discuss the implementation of our algorithm. So this is a Julia code, where the first pane represents the code and the pane at the bottom represents the Julia REPL. So let me load the distributed module in Julia, which we will be using to make things faster, and most of the things that we do will be employing parallelism. So in this computer, we will be using 8 workers with 1 worker as the main dispatcher. And then let me load my AutoML pipeline package, which will be the building blocks in developing the algorithm. And then we will load the data frames package also to store our data in tabular format, and then the score function, and then the random seed, the random package for the seed. Then let's make sure that the abstract data frame will not truncate the columns, because we will be using the expression in columns to have a much better understanding of the pipeline signature. Now let's load the elements of our pipeline, and then let's collect all the scalars in one vector, all the structure in one vector, and all the learners in one vector. So let me run first this block, and then let me run these blocks. And then let's load a very simple data set. For the purpose of presentation, I picked iris data set because it's a small data set, so that we don't have to consume a lot of processing time to fit in the presentation within 25 minutes limit. So this iris data is composed of X features, which are all numeric, and then the target, which is basically, the target, which is a class of the different types of plants. So here's an example of a pipeline in using AutoML pipeline package. So let's start with the base normalized form of the data. So we normalize the data first by transforming all the categorical features into hot bit representation and combine it with the rest of the numerical features. Then whatever is the result of this normalization, we pipe it to the min-max, and then pipe it to PCA, and then pipe it to random forest. So this is a one block pipeline. And then whatever is this pipeline, we cross-validate it. So, and to find out the performance of this particular pipeline. We can change the min-max into norm, and then run it again and see how it performs. Or we can also change this to ICA, or we change the learner to ADA. And as you've noticed now, by changing the different elements of the pipeline, the performance also changes. So the main target that we have is to find the best combination of pipeline elements together with the best with the learner, so that the cross-validation performance is optimal. For the two block pipeline, we will use also the base the baseline normalized data set, wherein it's translated to numerical form, and then feed it to the two block pipeline. The first block is composed of the norm with ICA together with power transform with PCA, and then the result pipe to LSVC. And this is now passed to the cross-validation function for performance comparison. So now we can run this and find out its performance. So with this one block pipeline and two block pipeline, we can basically create a pipeline factory composed of one block and two blocks, so that we can list down all the possible combination of elements in a one block pipeline. So you will notice here that in this function, we use distributed loops to loop over the different learners and to the different structures and to the different scalars, and set up the baseline normalization where the categorical features are transformed to hot-bit encoded representation and then combined with the numerical features. And then this preparatory data set is piped to the one block pipeline, which is represented by SC for the scalar, XT for the structure, and then pipe to the learner. And then we extract the names of these elements and use it for our description of the signature of the pipeline. And then we return a data frame composed consisting of the signature of the pipeline and the actual pipeline structure that we can evaluate later. So if we run this function, passing the scalars, the group of extractors and the learners, and store it to a one block result. This is done in parallel, so it's fast. So you will see that there are 144 different pipeline combinations that we have with different pipeline elements using one block pipeline. The first column is the signature, and the second column is the actual pipeline object. So now we can actually access one of the pipeline. For example, we would like to know the performance of the first pipeline. So we pass the first pipeline with the data set and cross-validate it. We can also check the second pipeline performance or the 144th pipeline performance. The reason why it's 144 is that we have 6 scalars, including the no-op, and then 4 extractors, including the no-op, and 6 learners. So 6 times 4 times 6 is 144. Now, because we have the pipeline factory of one block, we can now create a function that receives these pipelines with the data set, and we loop over each of the row of these pipelines, and then we pass each of these pipeline to the cross-validate function, assign it to a performance variable, and then we access the mean and their standard deviation, including their description, which is their signature. And we do this in parallel to evaluate them. So now let's create this function and let's pass the pipeline data frame, the data set, to evaluate each of this pipeline. So let's sort them and let's show all the result. So we start at the worst one, which is add a boost, 66. And the best one is gradient boosting at 98% accuracy. So you'll notice that with the different combination of pipeline elements and learners, you have a different performance. One block pipeline seems good enough, but in many data sets that we tried to, to experiment, one block pipeline is suboptimal. So the next logical thing is to extend this into a 2-block pipeline. And hopefully the 2-block pipeline will be much better. So now you will have 2 extractors to represent the first block and the second block, and 2 scalars to represent the first block and second block. The learner is still the same. So now you have, you still have to do some kind of normalization for the preparatory data set. So you transform everything just in case you have categorical values into heartbeat encoded representation, and then combine it with the rest of the numerical features, and then you feed it to the 2-block pipeline. So SC1 represent the first set of scalars, and then pipe to XT1, which is the first set of extractors, combined with the second set of scalars, which is here, and the second set of structure, which is here. So you have several distributed loops, and then finally we pipe it to LR. And then here the statements are just to access their names, shorter names, so that we can make a summary of the signature of this pipeline and then place them in a data frame. So if we do that, we now have more pipeline elements, which is, I think, around 3,000 plus. The reason why it's 3,000 is that you have like now 6 times 6 scalars, 4 times 4 extractors times 6 learners. Oops, sorry. 6 times 6 times 4. Yeah, so 3,456. So just imagine now, you can loop over these different pipelines and run each one of this pipeline and find out which of this pipeline is the best. I did that in some of the data sets, so let me show you. I cannot show you the runs here because it will take some time, more than an hour. So let's open the data set. So I have here set of data set that I can compare with the best pipeline from the, from the different, from the best algorithms. For example, for this data set, gesture segmentation, the best that we got using by evaluating 3,000 plus pipelines is 30.21 accuracy, mean accuracy error. And the best is 32.78 from Teapot. So our algorithm is much better actually. And it runs less than 4 hour time budget. And this runs with 4 hour time budget. Ours is less than 4 hours. Some of them are less than 1 hour actually. Small difference. And then for the eucalyptus, 35.41 versus 33.74. So again, if you use the 2-block pipeline with 3,000 plus pipelines to evaluate, it's competitive enough. But the question is that, can we do better by reducing the search space? Because this is still a lot of search space, relatively speaking. So one thing that we notice is that if you gonna examine the signature of this pipeline, you will notice that the model random forest dominates the other models, regardless of the combination of the pipelines. Random forest is much better, relatively speaking, from the GB and the rest. And here, LSVC performs worse no matter what kind of preprocessing order or pipeline components it has. So it seems to indicate that we have to pick the best model first, because the best model drives is more significant than the pipelines. Again, here Adabus performs worse, while here all SVC, RBF, and and linear SVC performs very well. The same with the other data sets. Like here, LSVC dominates the other learners, regardless of whatever pipeline it is using, while decision tree is worse, regardless of whatever pipeline it is using. Here, random forest dominates, and here, gradient boost dominates the solution. So with this insight, we can now think that to simplify our solution into stages. So first, we do model selection. And the problem is that what kind of pipeline do we use? So we can start with an arbitrary pipeline with any pipeline and loop over the different learners and evaluate the performance for that pipeline. So here we create a model selection pipeline which receives the set of learners, and then we loop over the learners, and then we just specify again this is the preparatory data processing step. And then we feed it to robust scaler with PCA, and then feed it to the learner. And then that's it. So we use this arbitrary pipeline as a surrogate pipeline to evaluate the different learners. So let's create these pipeline components. So here, we only have to deal with 6 pipelines. And then we compare which of these learners is the best and choose it to search for the pipelines in the next step. So let's now evaluate these pipelines. So we pass the pipelines with X and Y. using tenfold cross-validation and sort the result based on mean to find out which of these learners is the best. Again, we try to make it faster by using parallel approach because each pipeline is independent. So they don't have to communicate with each other. So it can be parallelized. So here we find that RBF SVC is the best. So now we can use this RBF SVC as our input to the two-block pipeline factory with a set of scalars and extractors. But by this time, instead of passing all the learners, we just pass specifically one learner. So now this pipeline factory will only generate pipelines that include the RBF SVC. And now the number of pipelines is reduced from 3,000 plus to just 500 pipelines. And that reduction is like 6 times less. So 576 is doable in this presentation. So I can run this pipeline and find out the best solution. So we evaluate this pipeline and pass the data set and then sort the result again and then show all the results. So while it's running, let me show you some of the results that we have using this stage-wise technique. So now this result here, so let me load the original thing. So the pane above is the 3,000 pipelines, which is the exhaustive search, but this one is 500 pipelines, which is 500 plus pipelines, which is this the search by done in stages, model selection and then pipeline selection. You'll notice here that the result is very close to the exhaustive search, 30.46 versus 30.21, which is still better than TPOT, which is 32. And then for the soybean data set, I don't think it improved the bad solution of our algorithm because of the missing data. So it's still low, like 13.24 versus 13.42, which is not better than 6.59. But for the rest of the problem, it performs as good as the two block pipelines in the pane above. So here, 23.82 versus 24.69, which is still better than TPOT, which is 32.43. And then for GM1, 17.62 versus 17.67, so a slight difference versus 18.13. And then for the eucalyptus, you have 33.74 versus 33.4 and 35.41. So all in all, the performance is the performance of the stage-wise approach, or by doing model selection first, followed by pipeline search, is as good as the exhaustive search, and also sometimes better, or oftentimes better than the best algorithm in that is in the literature. So this is the result, the final result of the RBF SVC. As you've noticed now, the worst solution is 90, which is really still good. And the best solution that it found is, I think, 99. Yeah, so it can even reach 99% accuracy for the iris dataset. I will end my presentation. Thank you for your attention.